Okay, coming back to the lecture note, we defined the quantile regression parameter as using the least absolute deviation check function as the check function, and considering this check function, and we are going to minimize this expected check function. We will we know that the minimizer is the quantile. So in this case, we do not have any x, but in general, in a simpler case, you have this minimizer of the check function is quantile. And we are going to study what's going on there, and the same thing happens here. So minimizer of the check function in the linear model is the coefficient, true coefficient of the quantile regression model. So to study the properties of this check function and the following estimator, we will be differentiating the criterion function because it is minimization, and of course we are going to utilize the first order condition. So but we know it is differentiation is it is a continuous function, but it is clear that there is a kink in the check function, and the check function is differentiable everywhere but the kink point. The kink point 0, which is always 0, at 0 it is not differentiable. So this is a problem at some point, but it may not be a problem elsewhere because just it is one point. So you can say that the check function is differentiable almost everywhere, almost surely, but one point is absolutely not differentiable. It is not differentiable. So the main problem here is Taylor theorem does not work. Taylor theorem is not working anymore, or so then many things, all the theory, previous asymptotic normality theory breaks down. However, in the end, we have almost the same result as before, but we have to show the proof must be different. And this technique, the technique we use in the proof, is very important in econometrics. In econometric theory, this kind of nonlinear problem, like non-smoothness problem, arises in some cases, some important cases. And if you are going to major in econometric theory, knowing this technique is very important. So let me explain. First, we will define the gradient function psi. It's just a derivative. It is derivative, but when at epsilon equals to 0, I just did not specify here. It does not matter if epsilon equals to 0 is included here or here. Or you may assume that epsilon equals to 0 has a 0 point, 0. Anyhow, it does not matter. We have to define that more rigorously. To be more rigorous, we need to define this, but no matter what you use, does not matter. So I will ignore that. And so on the positive side, the derivative is gamma, like tau, and on the negative side, minus 1 minus tau, and which may be written in this way. Then think about the criterion function. The objective function is this form, and we would like to show that the minimizer of this objective function satisfies this condition. So this is the definition of the true parameter beta. So I defined it earlier. So the true parameter beta satisfies this relationship. Now let me show you how we get it. So differentiate. It is differentiate everywhere but one point, but it does not matter because when you take expectation, one point does not matter. So the differentiation goes inside the expectation, and then we use the gradient function times x, because when you differentiate with respect to beta, x will be multiplied, should be multiplied there. And you may write it this way. You can write this, so using the functional form of the gradient function, you get this equals to 0. And then from there, using the law of iterated expectations, just use the conditional expectation given x, and then take another expectation, and then x is fixed. This then expected value of this indicator function, conditional on x, becomes the conditional distribution function. This is the definition of conditional distribution function of y given x. So we may write it this way, and then this if beta satisfies this, then it will be tau. Also, this and this is equivalent. These two are equivalent equalities. So the first order condition is satisfied at the true parameter. Now, but now here, remember I did not use the disturbance term, but what's tricky here is, like, even if I am using expectation here, because we are minimizing the expected quantile, but you cannot use this because now we are using quantile regression. So the location normalization for the error term is made by a quantile like this. So the previous expected value of epsilon equals to 0 assumption is replaced by quantile epsilon equals to 0. So if it is not, so remember, expected value of epsilon is not 0 in quantile regression. This is often mistook by students. And also, okay, another important thing here is, because of this, now you cannot use demeaned variables. Demeaned variables not working anymore because we are using quantiles, not the mean. But then you may ask, can we make the quantile equal to 0 for every variables? That is not possible because the quantile operator is not linear. So because of the properties we discussed earlier, the demeaned variable approach is not working here. Just I'm telling you here. And for example, if you are interested in 0.9 quantile, it is top quantile, very like top 10%, then most of 90% of epsilon will be negative because its 90 percentile will be 0. That means the bottom 90% will be negative and top 10% is positive. Therefore, obviously, the mean equals to 0 is not true anymore. It does not hold. And similarly, many analyses based on the residuals do not work either, like R squared, F statistics, ANOVA, analysis of variance. Even though I did not teach this, they don't work. However, we may define something similar to them in a similar idea, but they cannot be used in the same way. You have to modify them. Without modification, R squared or F statistic is not true anymore. Does not work. Okay, anyhow, here I have shown that the true parameter satisfies the first order condition, and then that means, so the true parameter satisfies the first order condition, and then if we show that there is only one parameter, one value that satisfies the first order condition, then it implies that the minimizer is unique, right? So that can be done by checking the second order condition. The second order condition, by the way, before talking about the second order condition, remember, we may write it this way. So we will use this differentiation later. And the second order condition can be written in this way. This was, we learned, this is the result of the first order condition. So differentiated again, and then the differentiation goes inside the mean, and beta is only here. So differentiate with respect to beta, and then you get density. Conditional density is the result of the second order derivative. So you get expected value of conditional density xx prime. Now, so what we need to do here is we need to check this matrix. Matrix is strictly positive definite. Then if that is true, the second order condition is satisfied. There is only one unique minimizer, unique solution to the minimization problem, and the value that satisfies the first order condition is the unique minimizer. So we can conclude that the parameter we wanted to estimate is the unique minimizer. So that's the rationale here. And so we need to check this expected something. It is a matrix, and it should be strictly positive definite. And we may, like, so it's simple. You may write it, you may think it this way. It is always positive, and this is strictly positive definite. So I'm not going to prove this, but it is similar to the full rank condition about this. Exactly same thing. This is strictly positive definite. So this should be invariable, and then when this is invariable, it will be strictly positive definite. So now we have a stronger. We replace this matrix with this. Then this involves an additional component. So having a strictly positive definite for this guy is a stronger assumption, because even if xx prime is strictly positive definite, if the density is 0, then it is not strictly positive definite. So because of that, the density, it's slightly different, but it is usually fine, because it is natural to assume that the density is positive. Having a positive density is not restrictive, so it is often assumed is not a big problem. Of course, full rank assumption is mild, does not cause much problem. Okay, this is identification story, how we identify the quantile coefficient. And in the next lecture, I'm going to discuss the estimation and how we derive the asymptotic normality without using Taylor approximation. Okay, see you there. Bye.